So what we've done so far is that we can figure out what these equivalent circuits are to kind of model what a complicated network of resistors and independent sources, we can take a complicated network like that and reduce it down to a more simple network that has just one source and one resistor in it. Okay? The Thevenin equivalent is one voltage source, and the Norton equivalent is one current source. So far that's what we've done. And up till now, what I've given you is a way of dealing with the equivalent resistance part of that. That is to say, kill all the sources, kill all the independent sources, and evaluate what the equivalent resistance would be through the network with all the sources killed. Okay, so far, that's what we've done. And right at the end of our last talk, the question was asked, well, what do we do about dependent sources? Okay, and so not to disappoint, let's talk about that now, right? So with this little example that I show right here, it says, try finding your equivalent Thevenin resistance for this network. Let's just go ahead and at least take a stab at it using the technique that we just learned, okay, and see whether or not that makes any sense. Okay, so what would we do? Okay, again, kill all the sources. What does that look like? I should say, we don't kill all the sources. Okay, I want to be very clear on this point. Which sources do you kill? Only your independent sources. So what would that look like on this circuit? Because I had that voltage source there, anytime you have a voltage source, you replace that with a short circuit, just like a wire that's connected across there. So that's our little circuit that we have, right? And what I'm supposed to do, if I follow the kind of directions that I had for my first set of instructions up there, I'm supposed to find the equivalent resistance across that network. Okay? So what techniques do we have for finding equivalent resistances? Okay? Kind of probably your thought process up to this point has been, well, I need to figure out if I have any that are in parallel. And if I do, I can combine those. I have to figure out if I have any in series. If I do, I'll combine those. And I'll keep working through it until I find an overall equivalent resistance of the whole network. Right? That's kind of the technique that we showed you back in the freshman year. And, so maybe you're comfortable and say, yeah, that should work. What do you do first on this one? Do I have any resistors in parallel or in series with any other resistors? And I see a lot of thought going on. The answer is no. You don't have a single resistor in series with another resistor. You also don't have a single resistor in parallel with another resistor. You don't have anything like that you can do on this circuit. Plus, on top of that, you've got these dependent sources, and as you kind of look through your techniques of doing things, I wouldn't blame you if you're like, well, I don't have anything in my toolbox yet to deal with those dependent sources. Okay? So we need something else. We're not going to be able to do the exact set of rules that I had up here for cases where we've got dependent sources especially. But especially where, maybe a more general way to put it, maybe I'll say it this way. A more general way to put it is that if it's impossible for you to just kill the independent sources and find an equivalent resistance across the terminals, which it will be sometimes, if that's impossible, you can go to this next method that I'm calling, this is episode 2 where I'm telling you about this second method. Okay? So, let me give you an updated set of rules. If you have dependent sources present in your circuit, instead of going about trying to figure out what your equivalent resistance is just based on like finding equivalent resistance across the terminals with your independent sources killed, now you go, all right, well, I can't do that, but I can figure out both my Thevenin voltage and my Norton current. Right? I could do both just like I did on the last example, right? I can do both of those analytical techniques to figure out both my Thevenin voltage and my Norton current, and the equivalent resistance for your Thevenin or Norton circuits is just going to be the ratio of your Thevenin voltage to your Norton current. So as long as you can do both of those, you can still figure out what your R sub TH value needs to be, as long as you can figure out both your Thevenin voltage as well as your Norton current. Okay? Shall we do that for this one where it has dependent sources in it? I know you're excited about it. You're super excited. Okay. And I tell you what I'm going to do for this example problem, because, again, we have to bring in some kind of a circuit analysis technique even to do what I'm suggesting here. I'm going to suggest that for this one, let's do nodal analysis. All right? So where do I have my nodes for my original circuit right here? Tell you what, I'm going to make a copy of it, because I'm going to want an undisturbed one here in a second. So let me make a copy, and I'll leave it over here. Okay. All right, so what do I need to do to figure out my Thevenin voltage across terminals A, B, and I'm using nodal? Remember what our first step was with nodal? Define your nodes, which also includes defining a ground node, right? So let me just go ahead and call this down here. I'm going to say that's my ground node. And what else? We call this V1. Let me call this V2. Okay. Do I have any other nodes? Okay, there's a big node up here at the top that I will call V3. I'll call that voltage on that node up there V3. And those are all relative to the ground node. Okay? So that's kind of a starting point. Then what should I do with my nodal analysis technique? Should I identify maybe any supernodes? Okay, where do I have supernodes when I do nodal analysis? Okay? Yeah, you look for the voltage sources. And for this, it's voltage sources that are either independent or dependent. You can use both of those whenever you start talking about finding supernodes, or, and when you're talking about meshes, you can use either independent or dependent current sources when you find super meshes, okay? But anyway, for supernodes, we look for both independent and dependent voltage sources. Where do I have those? Okay, what I'm going to say is I have an actual node up here for V3, but I go right across all of my voltage sources, right? Anytime I have a voltage source, I'm just going to go right across those whenever I identify my supernode. Okay, with me so far? So that would be a place, so that's a big supernode on which I am going to do KCL analysis, right? And I tell you what, I do want to do that, but before I get to writing that equation, I notice one thing that I have right here, and that is one of my terms at least is going to include this Ix value, right? Is there any way for me to maybe simplify this process by first coming up with a relationship for Ix? Okay. I see a few of you nodding, right? The answer is yes, okay, because I've identified a voltage across the 220 ohm resistor in terms of V3 and V1, right? And I know that resistance value of 220. That means that Ix is going to be what? V3 minus V1 over 220 ohms. Okay? And I just went ahead and did that relationship right there because that might be an easy substitution for me to make as I start going through my actual nodal equation. Okay? So I just kind of preempted it and said, I can find Ix. That's what it is in terms of my voltages. Right? Okay, now let me do a sum of currents in and out of my supernode that I identified up there. Okay? So where's one of the paths that a current could flow? I'm going to take outward flow as being positive. In other words, currents that leave the node, the supernode, I'm going to take those as being positive. Okay? So one of the things I see is that I actually have a current entering the node over here that is going to be 3.5 times Ix. Okay? Because it's entering, I'm going to count that as minus 3.5 times Ix, but let me go ahead and do this substitution. 3.5 times what? V3 minus V1 over 220 ohms. That takes care of the flow that comes in on this dependent current source. Okay? Where else do I have currents entering or exiting the supernode? I would say V2, that I've got this voltage of V2 across for the 470 ohm resistor, so that would be a current leaving based on V2 over 470 ohms. Okay? Where else do I have currents entering or leaving the big supernode? I have one across the 1 kilo ohm resistor, right? So that would be plus V3 over 1,000 ohms. Okay? Anywhere else that I would have currents entering or leaving my big supernode? Okay? Now, this is a good one to kind of think about. What about the 220? Well, you could count it, but if you look at it, the 220 ohm resistor has both of its legs on the same supernode, right? So if I count current as leaving the supernode, it's just going to immediately enter the supernode in another location, right? So I'm just not going to count it because that's kind of a pointless endeavor, because you'll add and subtract the same value from your sum. Does that make sense? Okay, so I'm just going to say, I think we're done. That is all of the currents that enter and leave the supernode. All right, how many variables do I have? 3 variables, right? V1, V2, and V3. That means I probably want to come up with a couple more equations. Where do I look for those equations? Voltage sources. That's right, both the independent ones and the dependent ones. So let me do the easier one first. That is the independent one. How do I get that one in the game? V1 minus V2 is what? 2.5 volts. Okay. Now I've got 2 equations in 3 unknowns. So that's a better scenario. What else do I need to do? Okay. The dependent source says that V3 minus V2 will be what? 2 kilo ohms times Ix. What's Ix? Okay, I tell you what, I did this on the other one as well. Let me go ahead and substitute in this as 2,000 ohms times Ix. Okay, now I think you said that Ix, we already found that up here, of V3 minus V1 over 220 ohms. These 3 equations right here represent a system of 3 equations in 3 unknowns. It is a linear system of 3 equations and 3 unknowns. And so if you had a mind to, you could take these and boil out the coefficients of V1, V2, and V3 for each equation, as well as any terms that would be moved to the right side of the equation. And you could enter this system of 3 by 3 in a FE-approved calculator and get your answers. I did that, and here's what I got. V1 winds up being 3.173 volts. V2 winds up being 0.674 volts. And V3 ends up being 3.483 volts. Okay, those are my results. Are any of those results especially meaningful to me? Okay, maybe I'll ask it a different way. What were we supposed to find? We're supposed to find an open circuit voltage, right? That's what we do with the Thevenin technique, open circuit voltage. Where is that open circuit voltage for this network? It's the voltage across terminals A and B, right? That's what we're trying to find, is the Thevenin equivalent across AB. And so with A and B unconnected to anything, I'm figuring out the voltage across them. Do I have that voltage represented anywhere in my results? I do, right? V3, another way of saying V3 is the voltage from the ground node to that upper node, right? So V3 is my Thevenin voltage. I didn't have to do any post-processing after I did kind of my nodal analysis. I just came up directly with what my Thevenin voltage was. Okay, 3.483 volts. Okay. Now, I can't come up with my total Thevenin equivalent yet because I don't know a equivalent resistance for my Thevenin circuit. That's the whole reason, or that's kind of the whole thing about this problem that makes it different than the last one we did, right, is that, you know, this one, you can't find that RTH beforehand. So what do we need to do? What we need to do now is figure out what is my short circuit current, right? That's the other half of doing this technique that I mentioned up here. Finding your Norton current is that's the short circuit current of the live network, meaning you short across the terminals like this, and then you figure out, when you do that, how much current flows. That current that flows is your Norton current. Okay? So that is what we need to do, is figure out that, you know, I sub NO for this circuit. And once we do, how does that help us find our equivalent circuits, either Thevenin or Norton? That gives us the denominator of this ratio, and that allows us to find R sub TH. Okay? All right, so now let's get into that and say, now that I've got that shorted across terminals A and B, will any current flow on my 1 kilo ohm resistor? Why not? I see a lot of heads saying no. Why not? It's going to go your path of least resistance. You just made a path of zero resistance over here. So that means no current is going to flow on this leg. So that means once I short it, I can simplify my circuit by getting rid of that leg. All right, because there's not going to be any current that flows on it anyway. Okay? Now that actually makes this incredibly interesting, because let me trace the ground node. Like on the last one I said, let's make this my ground node. Okay? Let's trace my ground node. It's all of this, all the way up to here. Okay? All the way up there. Now let's trace the ground node, keeping in mind that we're also going to use the supernode technique. So now instead of tracing just the ground node, let me trace the supernode that the ground is a part of. Okay? With me on that? So I'm going to trace across here, which I go right across that one because it's a voltage source. Trace over here and over there. That is my supernode. Can I do any KCL equations if I'm going to treat that as a supernode? No, why not? There aren't even a pair of nodes. There isn't even a pair of nodes for me to think about current flowing from one node to another across some path or another. Well, that's kind of interesting. Does that keep us from being able to analyze this circuit? Okay. As you might suspect, it does not, but we have to start thinking about what are our other relationships. Okay? So like what? First of all, V3 no longer exists. Right? Remember I started out with V3 up here. I just connected that up to ground. So that means there is no voltage level up there. Right? So what are my only other remaining voltages that I can have? V1 and V2, right? And can I make some relationships for V1 and V2? Sure, right? My relationship of V1 minus V2 is equal to 2.5 volts. That's still valid, right? What other relationships can I do? Can I do that for the other voltage source, the dependent one? Yeah, I can do what? Okay. V2 is going to be equal to, now be careful because the polarity of this source, V2 is actually going to be equal to negative 2,000 ohms. Right? Negative because the positive's on the ground terminal, right, or ground node, right? And the negative goes up to where V2 is. That's why I put that negative sign right here. 2,000 ohms times what? IX, and IX, does it still behave the same way? Or is it kind of different now? It's kind of different because it now flows through this 220 ohm resistor, right? So I would say IX now, actually maybe kind of pause on this equation that I'm writing. What is IX going to be? Negative V1 over 220 ohms. So that means that I can substitute that in right here and say this is going to be negative V1 over 220 ohms. Okay? Yes, ma'am. Okay, so why do I use negative V1 for this equation up here? Is that your question? Yeah. So the reason I do that is that I defined IX as going this direction from ground up to the V1, right? If V1 is positive relative to ground, current would actually flow that way. If V1 had a positive value relative to ground, the current would actually be flowing from that positive value to the zero value, right? And because IX points opposite of the direction it should be there, I have to use a negative when I'm defining my IX over here with V1 relative to ground. Okay, so that's why that negative is there. The other negative is there because of the direction of this dependent current source, right? Because this dependent current source is saying V2 will have a negative voltage relative to ground because of how that current or that voltage source is oriented. Okay, so this pair of equations right here actually represents a 2x2 system that you can solve, right? And you end up with that, let's see, I think I've got them here. V1 winds up being negative 0.309 volts. And V2 ends up being negative 2.809 volts. And I missed my negative there. Okay? Good so far, but does that give us what we need? Okay? It's a nice step along the way to what we need, but what is it we're trying to find with coming up with our Norton equivalent? We're trying to find that INO, right? This thing up here. neither V1 nor V2 directly gives me that, right? So I have to do something to figure out what is my Norton current. What do you suggest? Okay. He wants to know, can I just find negative Ix? Okay. I would say no, because we don't know what the current is through the dependent voltage source. Because I think what you're trying to get at is based on this node up here, right? And that's not going to work because we don't know what the voltage is on that dependent source. But having said that, you are on a good track as far as thinking about doing something, okay? The track you should probably be thinking on is we have Kirchhoff's current law. And we can apply that at any node that we want, right? I'm going to suggest that we apply Kirchhoff's current law basically where this node branches right here. Okay? Let me show you what that looks like. Let's count, I don't know, you want to count entering or exiting as positive? Doesn't matter to me. Exiting, okay. Let's count exiting that node as positive. What I'm going to have is 3.5 times Ix. What's Ix? Okay. So this will be negative. Okay. Now, it's going to be negative 0.309 volts over 220 ohms. You see where my negatives came from there? Okay. It says 3.5 times Ix, but Ix is negative V1 over 220, but V1 is negative 0.309 volts. So that's where the two negatives. One negative came from right here. That one wound up right here. The other negative came from the fact that once I solved for V1, it came out negative. Okay, so that's how much current is leaving that node on that leg. How much current leaves the purple node right there on the leg going up toward V2? Okay, keep in mind, if V2 was positive, it would have a current that would flow that direction. If V2 is positive relative to ground, it would flow in that direction. Because of that, I'm going to say that looks like an entering current, so I'm going to take that as a negative because it's entering that node, and it's going to be based on V2 over 470 ohms. Okay? But what is V2? Okay. And then what? We're taking exiting or entering as positive. Exiting, right? All of this, we were exiting positive. So I'm going to take INO exiting positive. But what did I say INO looks like flowing from A to B? It looks like that's actually going to be entering, right? So I'm going to say that's minus INO. And that is my Kirchhoff's current equation for that node right there. Okay? Nothing is unknown except INO. So once I actually go to plugging all that in, INO winds up being 0.089 amps. All right. 10.89 milliamps, if you want to think of it that way. Now what? Now if I want to do the equivalent, Norton equivalent and the Thevenin equivalent, all I need is RTH. RTH is just going to be equal to the ratio of VTH over INO, which is going to be 3.483 volts. over 0.01089 amps, and this winds up being 319.7 is what I've got here, ohms. Okay, and that gives me everything I need to be able to construct my equivalent Thevenin and Norton circuits. The equivalent Thevenin circuit would look like this, where I have 3.483 volts going through a resistor here of 319.7 ohms. Okay, that would be the equivalent Thevenin circuit. So maybe I'll box that, because that was actually supposed to be the thing I was coming up with, right? And then the equivalent Norton circuit would be like this, where we have 0.01089 amps going in parallel with my resistance of 319.7 ohms. Not bad, huh? All right. Any questions? I don't want to make you sad, but there is another category of circuit for which both of the methods that I've just shown you break down. Okay? And that is going to be the topic of the third episode in the Thevenin and Norton talks that we're doing here. Okay? But we're going to save that for the next time that we meet. Kind of what do you do? And I'll go ahead and give you a preview of it. It turns out that if you have purely resistive circuits, or circuits that amount to being purely resistive, it turns out that you can have circuits that have just dependent sources in them. If they only have dependent sources in them, they wind up typically being just a equivalent of a resistive circuit. Okay? If you have that kind of a case, then you are going to have zero Thevenin voltage and zero Thevenin or Norton current. So you can't do this method that I just showed you, because you're going to have zero values for those. Okay? Also, because you have your dependent sources potentially in those, because you may have those dependent sources, you might not be able to do the equivalent resistance technique that I mentioned in episode 1. So all that can end up breaking down. The good news is we do have a technique of dealing with that, and that's what I'm going to show you next time we meet. Okay? You got a question? All right, cool. All right, well, that's it for the day. Thank you for your attention. I'll see you later.